Welcome to today's Advanced Manufacturing Media webinar series. Our topic is how to reduce drill programming time. Hello, I'm Pat Wozniak, Senior Editor at Manufacturing Engineering Magazine, which is part of SME's Advanced Manufacturing Media. My beat includes covering developments in CNC controls, automation, and manufacturing software. Before we begin, I'd like to provide some background on what we'll be doing today. Our sponsor, Cimatron Group, is a leading developer of CAD/CAM software with more than 30 years' experience in providing manufacturing programming solutions. You will be able to ask questions during the presentation using the Q&A box that appears on the right side of the screen. If time runs out before we can get to all of your questions, we'll make sure to have the answers emailed to you. Portions of this webinar will include screen sharing and videos. As often happens over the internet, the quality of the presentation can be affected by the type of internet connection you have, the total bandwidth available to you, and the number of people accessing the bandwidth at that time. Mobile users will not be able to view the screen sharing, but they will be able to hear the audio portion. An archived version of the webinar, viewable no matter what device you are using, including the screen sharing, will be available later today. If you experience difficulty, please let us know via the Q&A app. Also, if you have questions about any other aspects of our webinars, please email me at pwozniak@sme.org. John Barnes, our presenter, is Technical Sales Account Manager for Cimatron. John has over 20 years in tooling and aerospace. While most of his time was in the tooling industry, he played an integral role in the manufacturing of the Themis telescope that surveyed Mars for the presence of water in 2001. While working for Cimatron, John has served many roles, including technical support, applications engineer, training, and sales. Now, here's John Barnes.
Thank you, Pat. So today we're going to talk about advanced drilling tools and techniques, automated NC drilling from 3-axis to 5-axis, automated gun drilling, programming and output, how feature recognition can vary among different CAM systems, and the difference between automatic versus automated drilling. We're also going to look at the use of stock and holder protection while drilling. First, a little bit about Cimatron. Cimatron is a world leader in CAD/CAM solutions with a focus on mold, tool, and die. Although we do have a lot of companies using Cimatron for aerospace and job shops, I would say that really our design focus is on tooling, but our NC is good in other aspects as well. Cimatron's been around for more than 30 years. We've got operations in more than 40 countries and more than 40,000 installations. According to a study done by the Aberdeen Group, it was found that shops that use Cimatron, both for design and manufacturing, are able to deliver tools quicker because of the concurrent approach that Cimatron offers. In this chart here, the one to the left that shows 8.7, it says best in class. What that means is, and this was true back in the 90s when I started in the trade, companies would search out the best software for 2D design, then for surfacing, then for cutter pass. They would try to get the best software for each of those departments, and we call that best in class. So even if a shop has the best in class software, it's not really as good as having an integrated system that's able to be associative and allow concurrent working. So drilling has been around for more than 6,000 years. I've got a little picture here of an Egyptian using a bow drill. I thought that was pretty interesting. And metalworking has seen a lot of improvements. Solid carbide drills really dramatically improve the efficiency, although they are expensive. We're going to look at how tool choice is very specific to the application and material. The technique is very critical, both to the tool life and to the accuracy of the holes. Not all solid carbide drills are the same. We're going to look at that a little bit. And I'm not claiming to be a tooling expert. I do recommend that you guys consult with your tooling vendors. We're going to go over a wide range of different tools, and I'll explain things the best I can. Okay, on the first slide here, these are some of the tools that I was researching for this project, and some of these I found to be pretty interesting. In the upper left, I've got a tool offered by Ingersoll. This would be for doing a tap drill and a chamfer for what I would consider to be like an eye bolt hole, but really any kind of threaded blind hole could be made in this way. And of course, with the through the spindle coolant, we don't do any pecking, which is kind of what this presentation surrounds, is the ability to just blast through steel without doing any kind of pecking. Underneath that, there's a picture of a chamfer ring being mounted to a drill, and I know this is kind of more of a production type application, and most of my customers are mold shops and die shops, but I think that today the line is really blurring between production machining and one-off machining. So even the practices that we would have said, well, that's really a production tool, I think is having more and more of a place in the job shops and mold shops. Up here at the top, I've got there's some 3 flute tools that I found from Fullerton and OSG. There's some really nice advantages to 3 flute drills. One thing is that it's able to be more self-centering because of it being 3 fluted. It tends to not work hard as much, and of course you can feed it quicker because you've got 3 teeth doing the work. And later on we're going to look at a video of that tool in action. Underneath that is a pretty unique tool. This one, of course, is an indexable tool, and it's got a little insert there to do the thread milling and to do the chamfer, and I thought that was a pretty impressive tool. Over on the right, there's some micro drills, and you can see here it says the world's smallest coolant drill, or world's smallest coolant through the drill at 20 thousandths in diameter. And I think that's just really amazing that you can have a coolant being put through the drill at that diameter. And there's also a picture there of some really small micro gun drills. And this bottom one is claiming it can drill 30 times the diameter in depth and 55 Rockwell material, which again is just really, really impressive. Okay, so I'd like to talk about the unique geometry these tools have. This example here, again, it's a micro drill. I know that it's zoomed in pretty good, maybe hard to see, but there's just a lot about this tool that's been really highly engineered for maximum efficiency. And I'm not trying to tout any one tool vendor. All of the tooling suppliers go through rigorous engineering in order to develop the best possible, drilling condition. But there's just a lot going on here with this drill that makes it a special purpose drill. And the other thing that I've found out in my research is that, and again, I'm going to speak in generalities. I know that there was not always a black and white when it comes to some of these applications, but generally speaking, if you're going to be drilling with a drill that's under 100 thousandths, probably you should be considering using a spot drill. And then I think over 1/8 of an inch, depending on what length the drill is, probably maybe you don't need a spot drill. But again, I highly recommend you consult your tooling vendor. But I'm going to show you some differences here on the next page. What this one is showing is that for a tool, and let's see what size tool we're talking about here. This is a 6 thousandths diameter drill. And on the left, the picture shows that a spot drill is used, and that hole was kept on center. It's a nice round hole. And to the right, this shows when a spot drill is not used, and you can see that the outside of the hole is not very nice, and it's not even very round. The chart below that is showing the positional accuracy. So again, if you're dealing with a really small drill, probably you're going to need to center drill it if you want to have the location and the diameter accurate. Okay, and on this slide, we're looking at the cutting performance. Here, we're showing that non-peck drilling is possible when drilling 3 inches deep at a 100 thousandths diameter drill. And there's some speeds and feeds there below. I don't want to get too much involved in that. Probably you guys can see it. Also here is the comparison of this type of drill versus a 1 flute gun drill. And you can see that with this carbide drill being 2 fluted, it's able to process the hole in about 8 seconds, whereas a gun drill processed the hole in 77 seconds. So it's quite a bit faster, and I wish that I had a third bar graph here to show how long that hole would take if we were using a high-speed steel drill with pecking, but I think you guys all have a good idea how much longer that would be. Okay, next, a lot of these tools are going to require a pilot hole in order to keep the tool engaged. And I mean, this was always true of gun drills, but even with the solid carbide tools, when you get a diameter to length ratio, again speaking in generalities, but probably above 5 times the diameter, you're probably going to want to have a pilot hole in place to keep that drill on center and on size. Here we see a couple different geometries. On the left, we're showing geometry that's well suited for steel, and on the right, there's geometry that's well suited for aluminum. And again, I'm just trying to point out the differences that there's a lot of engineering done to really fit everything about this tool to its application and material. In fact, I found this slide to be very interesting. Here we can see that computerized flow simulation was used to determine the best position of the coolant holes. And in this particular drill, there's 2 coolant holes per flute. And I believe the next slide is going to show us if you can get the coolant holes positioned properly and get the lubrication as it should be, then you'll not be gumming up the drill as much with the aluminum. So again, a lot of engineering is going into the design of these tools. Okay, now here I'm trying to show a mold making application. This particular drill claims to be well suited for mold making, and the idea is that we ought to be able to drill the holes without requiring any reaming, and maybe it's possible to eliminate wire EDM for some of the small ejector pin holes. Surely each application has its advantages and disadvantages, but the point is that with the technology we have today in drilling, probably it's worth at least asking the question, could we drill these rather than have them wire EDM? Okay, so the next few slides are just going to be some examples of cutting performance. We're going to look at the tolerance for size, the surface roughness. In this example, I believe we're using a 5mm drill, and this shows a little range of the tolerance. So it's holding a nice tight group for size, and we're holding a nice tight group down here for the surface roughness. Here we're seeing some examples of the chips at different inches per revolution. And over here you can kind of get a feel for what kind of RPM, feed rate, and surface speed per minute that we're getting. This is, again, the same conditions in a chromium alloy steel. And here's one with a die-cast mold steel of 45 Rockwell. We're looking at a 236 diameter drill, drilling 4.5 inches deep, and it's moving right along pretty good. And here's a mold steel at 55 Rockwell, and we can see that based on the number of holes, what kind of wear we're getting versus a conventional drill. Okay, next we're going to look at the different operations. So for coming in on a flat face, again, speaking in generalities, probably if the diameter to length ratio is less than 5, maybe we don't need a center drill or a pilot, but depending on the application, if the drill requires deep hole, probably we're going to be at least drilling the pilot hole. Maybe a center drill won't be necessary, but we're going to do a pilot hole. And generally speaking, the pilot hole should be about 1 times the diameter. And then when we bring in the longer drill, it's very important that the RPM is not real high. We can't have the drill whipping around. So what we want to do is we want to slow the RPM down to a couple hundred RPMs, enter the hole, come down, feed down to maybe 50 thousandths away, and then turn the RPM up to full speed, and then drill continuously through the hole. And prior to breaking out, we want to slow down the feed rate, and then we want to slow the RPM down as we come out of the hole. So, and then of course repeat this process. So this is going to require some unique settings for programming, because CAN cycles don't really handle this type of operation. And here's an example of irregular face drilling where something like this is going to require machining, maybe doing like a circle milling and establish a flat, and then drill the pilot hole, and then send the long drill in, and same thing, slow down prior to breaking through. So we've got all these different conditions that we want to satisfy here. Also, with these type of drills, we want to have a minimum distance here for chip evacuation, and they're saying that they want to have the diameter of the drill times 1.5 for distance here to make sure that there's adequate chip evacuation possible. And over here we're showing interrupted cutting, and we definitely want to slow the drill down before it breaks out through this interrupted cut. And at the example below, of course, that's going to require machining. You can't start a drill in that condition without machining the hole. The third illustration here shows a step tool. When I see this, I think about a counterboard water line, like in a mold application. And I actually did run a boring mill for quite a few years in my early 20s. And I remember that in a hole like this, probably I would have drilled the water line first and then threw a big high-speed steel drill in there and just chased that smaller diameter. Well, with the carbide drills, we don't want to process it that way. We would actually want to process the large diameter first and then the small diameter second. So the order is very important when using these types of drills. And again, the last illustration is just saying that we need to have the feed rate reduced prior to breaking out through the hole. So these are all very unique circumstances that require unique programming. And we're going to look at how Cimatron can address a lot of these unique situations. Here's a few more examples. Pardon me while I find my slide. I can't see the text here. It's kind of small. Okay, so for a cross line like this, the indexable drills, we want to slow them down to a quarter of the normal feed rate. Solid carbide, we want to slow down to a quarter of the normal feed rate. And the indexable drills, the exchangeable tip drills really aren't recommended for those type of cross holes unless the diameter is much bigger that it's crossing over. And here, of course, if you're trying to drill on an asymmetrical surface, it's going to require machining like we discussed earlier. Although I think in this picture showing that if the angle is enough to not obstruct the flute and the drill is stubby enough, probably you can get away with a situation like this. Again, it's very specific to the application. Okay, I'd like to give a special thanks to the Tool Company for allowing me to do this video. This is their 3-tooth aluma drill, and of course it's drilling in aluminum. But what I thought was interesting here is that we don't have the spindle coolant. We're just using a regular coolant line, and you can see we're blasting through that quite fast. And the 3-tooth drill, like I said, is a really nice drill for staying on location, staying on size, processing it quickly. So I think that even if you don't have the latest machining centers with the coolant, doesn't mean you can't take advantage of some of this technology. Okay, now let's take a look at some of the software. Okay, in this example, I've got a insert that has water lines, and I want to, of course, drill all the water lines with solid carbide drills, and I want to process the bottom holes, which are a 1/2-13 tap. So I'm going to go into the drilling. And I'm going to choose automated drill 5X. So of course we're making the assumption that this is going on a 5-axis mill. And I'm going to pick the surfaces that I want it to look at. And this could be used as a filter. I don't have to pick all the surfaces. I could choose just one side if I wanted to, obviously. And then I'm going to go to the group manager, and I'm going to box pick across these guys and accept that. And here it's giving me groups. So it says that these 4 holes are similar, and it's making a group out of them. Here's one. We'll just go through and I'll point out all these different groups. So it recognizes these as needing to be drilled, and it's giving them their own groups according to the geometric range. So now we're going to process them, and I'm going to choose Auto Fit Sequence. And let me just verify that it's looking in the right folder. And choose OK. It says for 9 groups, an appropriate sequence was found and attached. And we're going to save and calculate. And this is where we're going to start to talk about the difference between automatic versus automated. Actually, see, I put this in the wrong spot here. It should be below my stock model. I don't think it's going to affect me. Let's go into the navigator. And we'll play this and we'll talk about what's going on. Okay, so this is a 422 diameter drill, and I'm not doing any center drilling. It's
John,
just
we need to have you reshare your screen. Excuse me. Can you hit refresh on your screen share? Thank you.
Yeah. Are you seeing it now?
Yes.
Okay. Thank you. Yeah. Let me just start over there then, because I had put this in the wrong place anyways. Okay. So I'm going to go to drilling. 5-axis drill. I'm going to pick the part surfaces. And we're going to pick on the group manager. Okay, and over here on the right, it creates the groups according to the geometric range of the hole. Okay, and then I want to process those. So I do auto fit sequence. It tells me that it found 9 sequences for 9 groups. Okay, and then we're going to go into the navigator in order to see what's happened. Okay, and again, this is the 422 diameter drill coming in to process these half 13 blind holes. And I'm not doing any center drilling, and I'm not doing any pilot drilling because the diameter to length ratio is okay. And this is where we're going to start talking about automatic versus automated. The one thing that Cimatron does in this situation, this 422 diameter drill, as you know, is actually 0.4219. In fact, I think it's 0.42187. And so if you import this geometry through STEP or IGES, it might be 421 or 422 or 421 and 9/10. So we can set a range and we say whenever you encounter a hole from 421 to 422, this is how we want to process that hole. So it's not automatic programming where it has to fit the exact diameter and this has to be processed this exact way. It's more like we define a geometric range and we say this is the process that we want to use based on it fitting within this range of geometry. Now these water lines I am processing with a starter drill, but it's really because, well, it's for 2 reasons. Number one, I want to have a big chamfer lead in on these holes. I think that's an advantage. And secondly, you're going to see some logic being used here in a minute. This is the tap drill coming in and tapping these holes. But in a second, you're going to see that not all these holes are drilled in the same way. Even though I use the same sequence, the sequence can have logic built into it, and I'll explain that in just a second. Okay, right here. So I believe this is a 438 drill with a length to diameter ratio of 5. And with this hole, it's going down all the way because it can reach. And this hole is going to go down all the way because it can reach. But for the holes that are too long for this drill, it's still going to use this drill, but it's going to create the pilot. So it's going to go down 2 times the diameter, and it could be 1 times the diameter. That's the formula that I chose to use. But again, that's the flexibility of the software, that you can automate it to be however you want. You're not stuck with canned automation without any control over it. Okay, so this drill is going to go in, and it's going to either drill the hole completely, or it's going to at least give me a pilot depth for a longer drill. And you probably noticed that the software is optimizing the order of the drills. When it had the center drill and the spindle, it went in and center drilled everything. And now that it has the 438 tool with a 5 times length ratio, it's using that drill everywhere that it needs to be used and not wearing out the tool changer going through all the processes. Okay, so this one's almost done, and then you're going to see it use a longer drill. So this depth has logic in what tool it selects, and I'll explain that and show it in a minute a little bit better. But it's making these decisions for me based on what I told it I had available to the software. And you can set up any number of drills. In fact, when I first started preparing for this webinar, I had used a diameter to length ratio of 2, and then 5, and then 12, and then 20, and then 30. And I was showing it to a few people, and they said, "Are you crazy? Do you know how much these drills cost? Nobody's going to have that many drills at that price." So I went back and I changed it so that I only have a length to diameter ratio of a 5, I think a 20, and a 30. But again, it's whatever you want. You decide what drills you want to process with, and you set up the logic, and then you just apply the sequence, and it uses the logic that you build into it. And that's another thing I didn't mention was cost. Yes, these drills are expensive. They're a lot more expensive than a high-speed steel drill, but you have to consider the cost of the hole, not the cost of the drill. How long does it take to drill these holes, and amortize the cost of that drill across all the holes? Don't get sticker shock and say, "Well, that drill's too expensive. We're going to order the cheap high-speed steel ones." I understand that there's always limitations, with resources, but please consider the cost of the hole, not the cost of the drill. Okay, so let's go into this one, and I want to explain a little bit better what kind of logic I set up. Let's take this long drill, for instance. The long hole. I'm going to choose Modify Sequence so that you can see how I built it. So first of all, over here on the left, this is our geometric data. This all refers to the hole. And I can set a condition that says if there's stock on the top of the hole from 0 to 100, let that be a condition for it fitting to this geometry. Or I can say, don't worry about the stock. I'm not concerned about it. You also can set a range, and you can say that like, this is using from 437 to 438 and 5/10. Now I went a little bit over, and we all know that the nominal drill size here is 4375, but for whatever reason, the holes that I had were 4382, and I don't know why they were that diameter, and probably you guys run into this in the real world. Sometimes people draw things incorrectly, but you have the flexibility to set the range to whatever you know is going to work. Here's the depth from 850 to 13.15. Now 13.15 just happens to be the full depth that I can drill with my 30 length ratio drill. Anything more than that, and the 30 length isn't going to do it. So I went ahead and minimized that range. Now down here, these colors mean something. Actually, purple here is just a highlight, so don't worry about that color. But the red means that this one's not being used. So let me explain what the process is here. I'm using a 3/4 starter drill, and I can show you the top by clicking here, and I can show you the bottom by clicking here. And the bottom is just driven by parameters. So my bottom reference is DP. Of course, I've got a list here of what parameters I want to look at, and DP simply means the top of the hole. And I can even set a chamfer diameter to where I want to have a 562 chamfer on that 438 water line. I don't know what that depth is, and I don't care. What I care about is having a chamfer of 562 on that hole. Next is the 438 times 5 length ratio. And what this one says is drill, okay, the bottom reference is DP, which is still the top, and I'm saying let's drill 2 times the tool diameter. Okay, it's a formula. But I put a condition in here that says only allow this to happen if the hole depth is more than 2.2 in length. What's our hole length? We can look up here and we can see it. It is 11 inches. Okay, so if the hole were more than 2.2 inches, then I want to do the pilot drill. And then each one of these has a range. So this tool with a, well, this one's also a 5 length ratio, and the reason is because it may be possible that I can finish the hole with that drill. So if that's the case, I want to go ahead and finish the hole. That's what this line says. And then this one, of course, is the 15 length ratio, and here's the 30 length ratio. So I set up these conditions. I define a range this tool would be appropriate for, and then it just processes. It looks at the ranges, matches it to the conditions, and it programs the holes automatically. And it really works nice. I don't think there's anything else I need to show on this one. I've got some more things to show, and it has been already almost 45 minutes, so let me keep moving along. I'm going to close this one out. We don't need to save it, and I'm going to open another example. This one I think is pretty interesting. This is a core block for a mold, and I went ahead and did all the processing of the backside holes. I don't want to go through all this again for sake of time, but I processed the holes from the backside. And what I mean to say by that is that in a mold application, we've got all these ejector pin holes are relieved from the back, and they're reamed from the front. So I went ahead and processed all the clearance holes down to that depth. And again, I don't know what those depths are. The software knows. I just tell it, you know, go down to this value, and it is what it is. So that happens really quickly. But now I want to flip it over now, and I want to machine the top side down. And I actually did do roughing. I want to explain that I went ahead and roughed some steel out, did some more roughing, and a little more roughing. And at this point, I can show you what the remaining stock looks like. So I've got this milled down to say within 50 thousandths or 100 thousandths or whatever you want to make it. And well, there's one more thing I need to show you. I put little caps on these holes where they break out. Let me go to the sets and I'll show you what that looks like. Okay, so I put little, what I did is I created a bounded surface down here, and I copied it up here. It happened pretty quickly. And the reason I wanted that is so that I would get a nice flat area to circle mill on. So here I'm going to show, again, how I set up logic. And I said that if you have a breach condition, I want to do circle milling down to the top of the hole. And if you don't have a breach condition, or if that breach condition is, say, less than 50 thousandths, then don't circle mill it. So one sequence is either going to drill this hole and circle mill it first, and it's all dependent upon conditions and logic. So let me go back, and we'll process it, and I'll show you the result. Just make sure that we're looking at the stock. Here we are. We're going to pick all the part surfaces. And we're going to pick the holes. And we'll go to the top view to help facilitate that. We do the group manager. And I can box pick like this. And I'm going to hold down the shift key to deselect these ones because I don't want to process these ones right now. And again, I accept that. Over here, it builds all my groups. And we're just going to go ahead and do the auto fit sequence. Let me make sure I'm pointing to the right folder. And I am. Okay, and what you're going to see here is that the holes that had the breach are going to be circle milled, and the ones that had a very slight breach will not be circle milled. And if I show the remaining stock here, you can see that it takes into account how much stock is there when it creates the circle milling. And in fact, let me turn the stock off. Over here, you'll see that I've got an ejector pin hole at the bottom of this rib. So it's way down here. And even so, if I tell it to start the drilling process at the stock, let's do this. Oops. Okay, so the top of the hole is here, but it knows to start at the stock, and it starts up here. Same thing with the circle milling. You can see how I left that little flat there. I run this down, establish a flat, and then I can do the drilling operation after the circle milling. But the circle milling only happens where it needs it. Over here, this is the same hole, and I didn't get any circle milling because it was flat enough in the condition that I gave it. So there's a lot of logic being done here. And again, I can have it look at the length. I can have it use different length drills. However you can dream of processing something, you can build logic into these sequences and make it happen. We also talked about holder gouge checking. So let me real quickly open up another file, and we'll look at holder gouge checking. All right, and this is actually a little mistake that I made earlier that worked out nicely. Let me show you how I screwed up. We define a part, target part, and we say this is what the job is supposed to come off the mill looking like at the end of the day. And I accidentally grabbed one of my cap surfaces as my target part. Everybody can probably see that. This little guy is tagged, and I'm about to violate it here. It's going to be a real problem. All right, so I'm going to go ahead and execute this. And we should get an error message. And actually, there's going to be two error messages. This one may not be a problem now. It'll be a problem later when I verify it. But I know I'm going to have an issue where the 1/8 drill was not able to process this hole. Okay, I get this little interrupted symbol here. That interrupted symbol tells me to come down here and look for what's wrong. Excuse me. Down here, I know that it tells me that one of my drills doesn't have an adequate clear line. Right here. I don't know how well you guys can see this, but it says my carbide drill 1/8 times 5 should be greater than 1.7536. So let's go into my cutter list and let's look at my 1/8 times 5. Let's sort by diameter. Here's the 1/8 times 5, and currently my clear length is 1 5/8. So yes, it's not long enough. Let's make it 1.8 and say OK, and we'll reprocess it. And I should get a toolpath this time. Although I'm still going to have an issue over here when I go to simulate it. Okay, good. You got a toolpath. Again, you can see all the circle millings taking place. And I want to take this one into the machine simulator, and we'll look at what happens when we violate a part condition. All right, and let's see, we're going to use a machine. We'll just use a Haas. We're using the appropriate reference UCS. Let's go ahead and say OK. Now, I do know that I get another little message here about the y-axis being over-traveled. I think it has to do with the tool change position, which I think is a little bit carried away in the simulation. You actually see it go back to the tool change position. Well, what's interesting is that we're going to see the tool light up in red when it comes into contact with our part surface, so we know that we're having a gouge condition. Now, it's not really a gouge condition. It's because I screwed up and picked the wrong surface as part of the part surfaces, but it's a good little insurance policy. All right, let's get some of these windows out of my way. And we don't need to see the housing of the machine. And let's hit play. Okay, here it gives me a little message about exceeding the y-axis. That's okay. Wait, one more thing. There's one thing I want to change here that I thought was really nice. I want to set the color to be unique for each tool, because it really shows nicely where the circle milling left off, where the center drilling leaves off, the pilot drills, the full depth drills. It really helps to illustrate everything really nice. Okay, and that would be here under the simulation options, model, hopefully not that one. Here it is. Tool sequential number. This is really nice. Okay, sorry about that. Let me hit play again. Slow down. Sorry, I know this is probably jumpy for you guys. I'm trying to slow it down. There we go. So here's doing the circle milling. And we're going to see that red light up on the tool here pretty soon. See it? That red lighting up is telling me that I've got a gouge condition. And it should also be showing me here with little exclamation points. So we're doing gouge checking during the drilling operations, and it tells me if I'm violating any protected surfaces. It's almost done. In fact, this is the center drilling. See how I just punched a hole in there? Center drill, no spot drill required. Okay, and then this one is the pilot drill, I believe. There's the red tool lighting up saying, hey, you bumped into something. And then I also want to look at something else here. It's just about done. I think when this finishes up, we can see the last couple lines of code, and we can see where it actually reduced the feed rate prior to breaking out of the hole. Remember, the clearance holes were drilled from the back side, and now we're doing the ream hole from the top side, so we're going to be breaking out into the clearance hole. And you're going to see that in the code here where it slows down the feed rate. Yeah, I'll just speed it up. There's not much else to see here. Okay, I think right here. So for you guys that understand the code, take a look at this. We can see that we were drilling, this G01 is the drilling down to Z2.29 at 20 inches per minute. Then it drills down to Z.18. Then it lowers the feed rate down to 50%, and it finishes up the last half an inch. Now, why a half an inch? Well, it's because I told it to go a quarter of an inch past. So I'm going a quarter of an inch past, and it slowed down about 200 away from breaking through. And on the retract, you can see that the feed rate is 500% because I want to exit the hole at 500% of my feed rate. I don't see the spindle changing here, but that's just a matter of the post having it pass to the post processor, but trust me, it works. Okay, that's about all I really have to show on the software. Let me go back to the slide presentation here.
Hello, this is Pat Wozniak joining you again. If you can stick around for a bit, we can go past the 3 o'clock hour for questions. If you do have to go, the Q&A session will be included in the archive version that will be available later today. John, thank you very much for that informative session. We've received some questions, and it'd be nice to get to all of them before our time is up. John, here's a question. Does Cimatron have good modeling tools to put patches over holes?
Okay, yeah, so I kind of had showed how I had put some patches up on top, but that's a little bit different. Let me just show one more thing here real quick, because that's a great question. If I go back to the screen share, 1 second, here we go. Tell me if I don't get it turned on this time.
Okay.
Are you seeing my screen?
It's on now.
Okay, good. This will just take a second. I wanted to show one quick file. So here's an actual block that would require some patching to be put on. And the whole model is here. I've got the top skin kind of isolated. I can show you that all the surfaces are really there. I've just got it hidden is all. And with Cimatron, it's a little bit unique of a software. I can actually delete one of these surfaces. Let's do this. I'll do a remove geometry, and we'll take away this one surface. And if I show you the open edges on my job, these are all open edges. In other words, this is not a closed, watertight, solid model. It's just a bunch of surfaces that are stitched together. And even so, in fact, let me just point this one out real quick. This one, if I want to put a patch on, wouldn't just be a matter of, doing a chain around there and making a flat surface. There's a little bit to be done here. And if I told you that the webinar wasn't going to end until all these surfaces were patched, guys would probably start exiting quickly. But watch this. I'm going to go to the top view and go to faces, close open gaps, and pick all this stuff. And I can do new faces or same faces. I want same faces. And I'm going to close up all these holes in one operation. So everything you see in brown was just created automatically. And this is a real time saver for putting patches over over models. And it doesn't matter if this came from SolidWorks or Pro-E or CATIA. It could come in through IGES or STEP. We don't need the history to do things like this. Again, even though this isn't a closed model, I could do things like remove and extend, and I could say I want to get rid of this feature. I can make it go away. Or I could take the rounds off. I could do a remove and extend, and we'll just take off some of these radiuses. You could do extend object. You could push this wall up 1/4 of an inch. So it's really unique direct modeling on open solids. It's really a great modeling tool, and this is all available in the NC software.
John, here's another question. Are there design wizards that implement the cooling circuits?
Yeah, I mentioned earlier that Cimatron really is kind of more well known for being a good design software for molds and dies. We've got a really good wizard for mold design, which allows you to facilitate putting in ejector pins and cooling wizards, but it's not just for mold design. There's a lot of wizards that really help with any kind of tooling application.
Here's another one. Do you have any idea as to when E12 will be released in the U.S.? I'm loving some of the new features I'm seeing.
Yeah, I've been getting in trouble, I think, for saying when it's going to be released. I've been saying it was going to be released for a long time now. To be honest, version 12 has been released. The official version is done. Here in North America, we were waiting for an important patch to come before we were going to burn the DVDs, and that service pack has been released, and the DVD should be printed literally any day now. So I think that you guys should see them start showing up in the mail anytime.
Great. Can Cimatron identify automatically the tool according to the diameter of the model?
Not really. I would say that that's kind of more automatic programming versus automated programming. We don't want to pick the tool based on the diameter of the model. That becomes a little bit more automatic programming. I prefer to automate the other way around. I don't know if that makes sense or not, but no, we don't create the drill based on the hole. We match a drill with the geometric range of the hole and allow them to come together, appropriately.
Okay, John, we have time for about one more question. What else is new in Cimatron E12 for NC?
Well, one thing I'm really excited about is our new stock model. In version 11, we had two stock models. One was for faster calculation, and one was for higher accuracy. We have a lot of customers that use Cimatron for micromilling, and they needed a really super precise stock model. And we have companies that create big bumper fascia molds, and they don't need such a accurate stock model. So we had one that was really quick at calculating but wasn't super accurate, and we had one that was super accurate but wasn't quite so quick at calculating. And now in version 12, we have just one stock model that's good at both, and the quality is really amazing. I'm really excited about how great this new stock model is. It's true 5-axis, so any way that you flip the block around and over, it knows what was cut, even 180 degrees apart. So I guess for me, that's the really most important thing. We also had some really big improvements to our rest milling, and we can create really efficient tool paths, not just based on the previous tool diameter, but the stock that's being left over, and we can take additional passes. A lot of times in remachines, if you encounter a heavy stock condition, you break the tool. With the new enhancements we have in version 12, it'll recognize those heavy stock conditions and give you multiple passes so you don't have any tool breaking.
Thank you, John. Unfortunately, our time is almost up. All unanswered questions will be passed along to Cimatron, and you can expect a reply by email. The entire webinar will be available for replay by 4 p.m. Eastern Daylight Time, and you can access it by using the same sign-in link you used today. As John has shown, manufacturers can achieve great process improvements on the shop floor with advanced drilling techniques and the latest CAD/CAM automated programming solutions. SME and Advanced Manufacturing Media have a host of ways to keep in touch with the latest developments in software and manufacturing technology. For instance, our Motorized Vehicle Manufacturing Yearbook 2014 will be published in November. Our December issue of Manufacturing Engineering will include a feature article on CAD/CAM software for mold and die manufacturing. In addition, join us at FabTech 2014 on November 11th through 13th in Atlanta, where you can experience live equipment demonstrations and find cost-saving solutions. Thank you for joining us for this Advanced Manufacturing Media webinar. We hope you found it informative.